Hello, in lesson 3.3, compound interest, you'll learn to use the compound interest formula to solve financial literacy problems. So let's begin with what the compound interest formula is. Now, in your algebra classes, you learned that the compound interest formula was written like this. A, which stands for the account accumulated, the amount that's going to be in the account, is equal to P, which is your principal, the amount of money you initially invest, times 1 plus R, your interest rate R, raised to the power of T, which is your time. Now, in this example, T has to always be measured in years. So if it's not measured in years, we have to convert it to years to use that number for T. Now, this is again the most common application for exponential growth is an investment earning compound interest n times a year modeled by this formula. So using this formula on the left, we're going to create this formula which it compounds this interest R a variety number of times instead of just doing it once every year. So this formula on the right becomes this formula on this formula on the left becomes this formula right here, where n, this is the variation that we added, this n represents the number of times that it's compounded in a year. In your algebra classes, we take it for granted that it'll be only compounded once, so the value of n is going to only equal to 1, and dividing r by 1 gives us r, and multiplying t with 1 is just going to simply give you t. So that's why the formula looks like that. But we can compound our interest rate an n number of times, depending on what the account asks for. So, for example, let's say that Antonia invests $300 into an account with a 5% interest rate. If she makes no more deposits or withdrawals, let's find the account balance in 15 years if the interest rate is compounded with the following frequencies. Let's say we're going to compound this interest semi-annually, which means we're going to compound it twice in a year. So the value of n is going to equal to 2. So the account accumulated, the amount in the account is going to equal to P times 1 plus R divided by n raised to the T times n. So our principal is 300. Our rate is 5%, which 5% out of 100, 5 divided by 100 is equal to 0.05. 0.05 is going to divide it by 2, since we're going to compound it twice in a year. Now we're going to do this for 15 years, and that 15 is going to also be multiplied by 2 because we're going to again compound it twice every year. And this is going to give us again our account balance. And that total is approximately $629.27. Now let's say that our frequency, we're going to compound it on a monthly basis. And for example, B, we do it on a monthly basis. So now our value for n that we're going to use in this formula is going to be 12 because there's 12 months in 1 year. So we're going to compound it 12 times in 1 year. So our formula of A is equal to P times 1 plus R divided by n raised to the T times n power will be 300 times 1 plus 0.05 divided by 12 this time raised to the power of 15 times 12. And that amount is going to be a little bit more because we're compounding more times in 1 year. It's going to end up becoming a little bit more than the previous one, than the semi-annually, which is a total of $634.11. So there, this is how we use this formula and what this variant compounded rates or frequencies are implemented into this formula. How these numbers again are implemented into this formula. So let's look at another example. Let's say we're going to use a different, but we're going to now compound it on a quarterly and a daily basis. So if $2,500 is deposited into an account, earning 8.5%, how much will the account reach, assuming no other deposits or withdrawals are made from the account at the end of 25 years if the interest is compounded with the following frequencies? So let's start off with the part A, and let's say we do it quarterly. Well, in a year, that means we're going to do it 4 times. Quarterly means 4 times. So n will equal to 4. So plugging in the corresponding numbers into the formula, our initial amount of $2,500 will multiply 1 plus our interest rate of 8%, which is 8 out of 100, which is 0.08. That rate is going to be compounded 4 times. And we're going to raise that to 25 years times 4, which is going to approximately equal to $111, I'm sorry, with 62 cents. So that would be the account balance after 25 years if it's compounded 4 times in a year. Now let's say we're going to compound it on a daily basis. So at the end of every day, the interest gets compounded. So since there's 365 days in a year, that means we're going to do it 365 days for 25 years. So A will equal to, again, the initial amounts, 1 plus our interest rate, which is 0.08, and this 0.08 is going to be compounded 365 times. And we're going to do this for 25 years at a rate of 365 times a year. Now, this is going to approximately equal to a little bit more than the other one, then do it only 4 times a year. This is going to equal to $18,468.59. So you can clearly see that the more times we compound the interest in a year, the greater output we get and the more money the account is going to have in the same amount of time. So in 25 years, compounding it 4 times in 25 years is only going to give us $300 short, approximately $300 short than compounding it every single day. So the more you compound it, the more output you get from it. Now let's look at some other examples. Let's say that on a child's birthday, his parents deposited $500 into a trust fund that pays 3.2% interest compounded bi-monthly. So if no other deposit or withdrawals are made from this account, how much money will be in the account on the child's 25th birthday? So from 6 years old to the 25th birthday, the number of years that have passed is going to be 19. So 19 years have passed. Now, because we're going to compound it bi-monthly, well, there's 12 months in a year, but we're going to do it bi-monthly. It's going to be 2 times every month. So n will multiply 2 times every month times 12 months in a year. So that's going to be 24. So we're going to compound it 24 times in 1 year for 19 years. So plugging in plugging in the corresponding values, we get that the account balance is going to equal to the initial principal of $500 times 1 plus 3.2%, 3.2 out of 100, that's equal to 0.032. So 0.032 divided by 24 times raised to 19 years times 24 as well. So that's going to equal to approximately $918.01. So there's your answer. Now for the next question, we're going to suppose that a saving account offers a 0.4% interest rate compounded 30 times in a year. Now, if Diego opens an account with $750 and makes no other deposits or withdrawals, we want to know how much interest he will have after 10 years. So this one is asking us something different, not the account balance, but only the interest. So we're going to use again the same formula to figure out how much money is going to be in the account after 10 years, compounded 30 times. So this one is trying to tell us straightforward that the value of n is going to be 30, because we're going to compound it 30 times in a year, and our time is going to be 10 years. So the account balance that starts off with 750 gets multiplied with 1 plus 0.4% is 0.4 out of 100, which is 0.004. And that's going to be divided by 30. We're going to raise that value for 10 years multiplied with 30, which is going to approximately equal to $780 with 61 cents. This again, remember, is the accumulated balance, the accumulated accounts. So this is the balance in the account. This is the total amount of money that has been made in 10 years when it's compounded 10 times in a year. So to figure out how much interest is made, we just simply have to subtract the total amount that we currently now have by the amount that we started off with, and that's going to be a difference of $30.61. So this is the interest that was made in those 10 years if we compound it 30 times in a year. And there's your answer. Now, of course, we can also compound our interest an infinite number of times, a continuous amount of times. And if we do that, that changes again the formula overall. So let's assume that when we let the number of compounding n increase without bound, again doing it infinitely and continuously, this process approaches what is called a continuous compounding. So if we get this formula and replace the value of n, the number of compounds per year n, to mr, then the process is going to become as following. So as you see right here, I substitute in n with the value of mr. The r and the r cancel each other out, give me only 1. And if I split this up to a power function using my exponential rules and write it as such, I have 1 plus 1 over m raised to the m power. Well, look what happens when I raise m and I get m to become very, very big. Again, meaning I'm compounding it an unlimited number of times. So if I make m become a very, very big number, I'm going to see that this value here gets closer and closer to the number 81828, which is approximately Euler's number E. I get very, very close to this value of E, which means that if I replace this with this value, my formula then becomes that A is equal to P times E to the RT. Is the exact same formula that we used in identifying continuous growth or continuous decay from the lesson 3.2. So it's the exact same formula as a result, and this is how this formula is generated using again this logic. So let's use this formula to compound and apply it now to on continuous compound interest formulas and apply it to literacy, financial literacy problems. So let's look at example 5. Suppose that $800 is invested into an account of 6% interest at a 6% interest rate compounded continuously. If no other withdrawal deposits are made, let's find the balance in the account after 20 years. So A is going to equal to P times E to the RT power. And in this situation, R is obviously going to always be positive because it's growing. So we'll start with the $100. We'll multiply E, raise it to 6%, which is 6 out of 100, which is 0.06. So 0.06, and we're going to multiply it by 20 years. We're going to get that this is going to equal to a total that's approximately 2656, so 2656.09 with 9 cents. So this is what that is equal to. Let's do one more. Let's say Carl's investing $1,500 into a new retirement account, and he has two options. Option A is going to pay him 5.5% of annual interest compounded monthly, while account B is going to pay 2.7 annual interest compounded continuously. Let's determine which of these interest rates and compounding periods would be her best investment option. So let's see how Carol is going to make more money. Which account is going to give her more money? So with the first one, option A, because it's compounded monthly, we're going to use this formula here. And N is going to equal to 12 because we're going to compound it for 12 times in a year. So starting off with the $1,500, 1 plus account A is at 5.5%, which in decimal is 0.055, so 0.055, and we're going to compound it 12 times for 30 years, so 30 times 12. This is going to equal to approximately $7,781 with 8 cents. Now let's look at option B. Option B is going to pay 2.7% compounded continuously. So we'll use this formula for option B. We'll still use the $1,500, that's the initial amount. E will be raised to the 0.027 because it's 2.7%, and it's still going to be done for 30 years. This is going to equal to approximately $3,371 with 86 cents. And notice that even though this option B compounded continuously, it doesn't give us a larger number because of the interest rates. The rates, again, really diminish the amount of money that she can make with the second option. So in this situation, the better option would be option B. And specifically, option B is better by $4,409.22. That's how much better option B is. You'll make that much more money using that option instead of option A, instead of using option B. Well, that concludes again the last example on lesson 3.3. If you have any questions, please send me a message on Remind or email. And again, thank you for watching, and I hope